Hello students, good evening. So welcome to the session 11 of work, energy and power topic. So already in session 10, right, we started discussing about the idea of collisions. I mean, we have not really started discussing about the collisions, but we have started with the idea of what is the linear momentum and kinetic energy relation for a object or a moving particle, because those two things, right, we are going to be focusing exclusively when it comes to the study of these collisions. So in today's class what we'll do is we'll start with understanding of the collisions, and we'll see what are the classification that we have in terms of collision. So we'll classify the collisions in different categories so that we can study them better. Okay, so we'll start the idea of what is a collision. See, the moment we hear this word collision, right, what is that? I mean, there are a lot of things that will come to our mind, like say maybe, so what you see in the visualization here is what? Two celestial bodies. Maybe that's the kind of situation that will happen when it comes to the destruction of the planets or the any satellite or any celestial body, right? When they hit each other, what you see is they'll basically be I mean, smashing into one another, and that will probably lead to complete destruction of the body itself. Okay, so this is also a collision. Okay, similarly, when we look at a player, a person who is playing probably baseball, so he is falling onto the ground. You can see here. So when he is falling onto the ground, what is happening? His body is actually colliding with the ground. So that is also collision, right? So in the previous case, what we see is almost the planets, they are smashing into each other and they are getting completely destroyed. But here it is not happening. After hitting the ground, because of their training, etc., they'll ensure that not much damage will happen to them, and that guy is able to get up and then walk almost normally. Okay, this is also collision. What is it? The person is colliding with the ground. Now look at here. No, so what is happening? Two players, they are colliding with each other. Okay, so this is also a collision. So all these are right. So they are basically trying to give us an idea of what are all the things that we can categorize as collisions. Now you see here cars smashing into one another. This is also collision. Luckily here nobody has actually got injured. So even the car that has got tilted upside down, right? So the driver of the car is able to also come out safely. So this is also what example of collision. Correct. Now if you look at a small gas molecule which is inside the container, so you will study about it in the kinetic theory of gases chapter. Even in chemistry also you will talk about it in the states of matter chapter. So if you look at the gas molecule that is moving inside the container, right? So the gas molecule will undergo collision with other gas molecules as well as with the walls of the container. Okay, so that is something that we will be able to observe. But the interesting thing about this collision is the colliding molecule, right, will never be able to lose its energy completely. Means at no time it will be able to come to complete rest. Okay, why it happens, we will be able to understand better once we cover the types of collision. In fact, the collisions between gas molecules and collisions between a gas molecule with the walls of the container, they are going to be called as elastic collisions. So what is an elastic collision? We will be able to understand it once we cover the types of collision. But all these are what? These are all the examples of the collisions. So if you want to put it like a definition, okay, so how do we? Because these are all the general understanding, right? Okay, so this is also collision, that is also collision. We have seen some examples of collision, like a lot of things. You're hitting the ball with a bat, that is also collision. Okay, so you are throwing a ball to the wall, that is also collision. So all these are collisions. Okay, now when we even clap our hands, that is also collision, right? Both the hands are actually colliding with each other. So all these are what examples of the collision that we can think of. But let us actually go and see how we can define the collision phenomena. So the most important thing that we need to note here is the collision, right, is considered as an isolated event. We'll study, we'll discuss more about this word. What do you mean by this isolated event? Okay, so first let us read to the statement. This is probably the way we have to write the definition of a collision. So if at all these kind of questions are coming in the regular school kind of an examination. So what is it? We are defining collision as an isolated event in which a strong force of interaction acts between two or more bodies. So whichever bodies are engaging in the collision, right? There will be a strong interaction force that will be acting on these bodies for that short collision time. So during that collision time, the actual collision time, right, there will be a very strong interaction force. We will also be calling it as the impulsive force. So we'll also be calling it as what? The impulsive force or interaction force. Okay. So there will be a strong, means the magnitude of this force is going to be very high. We'll see what is the reason for that also. And this is going to be acting for that very short period of the collision. So the actual collision time will be typically in the range of maybe a millisecond or a microsecond. Depends upon the kind of collision that is engaged also. Okay. So the duration of the time as such will be very small. And as a result of this event, what we will be able to observe, because so when they are engaging in that event, so we should be able to see some changes, right? What we will be able to observe, we will be able to observe that the energies and momentum of these interacting particles may be changing. Like you see here, right? What is happening? The ball is going. So initially this is at rest. Okay, so we can even name them. So let's number them as what? 1 and 2. The ball 2 is at rest and ball 1 is moving. After collision, right, we'll see that both are moving, but probably with different velocities and different directions. They'll have different momentum. Okay, and energies also might be changing. So what is the observable change we can see for these particles engaged in the collision, right? We'll see that their energy means we're talking about the kinetic energy. Okay, their energy or the momentum values, they will be undergoing a change. So this is what we will observe as a noticeable change as a result of this collision event. Okay, now let us see why are we calling it as an isolated event. So isolated event means when this phenomena is occurring, right, when this collision phenomenon is occurring, it is supposed to be independent. So the phenomena, right, is supposed to be independent of any external. So this is supposed to be independent of any external influence. Means the collision phenomena, right, will be totally independent of any external factors. That is the reason why we will be calling it as an isolated event. Why it is so, we will be talking about it. So why the collision phenomena will be totally independent of the external influences, we will study about it. Okay, but this is how we are going to define the collision phenomena. Okay, and mostly in our purview, right, we'll try to study the collision of two objects. So we can also have collision of many objects, but most of the times, right, when we talk about the collision, we'll be referring to collision of two objects or two bodies. Okay, now collision, when we say collision of two particles, we're talking about the point masses, correct? When we say collision of two objects, what are we talking about? We're talking about the collision of two extended bodies. So here in our collisions, right, we will be looking at both the collisions of particles as well as the collisions of the extended bodies. Okay, but generally when we talk about the practical examples, right, what do we see? We'll see collision of extended bodies or the large objects, right? Okay, so this is about the idea of collision. Now when we think of collision, right, most of the times the examples also that we discussed, right, we were seeing that there is actually a physical contact that is there. So during the collision time or collision process, we have observed, like, whether it is the person falling onto the ground or two people colliding with each other or cars smashing onto one another. In all these cases, what are we seeing? There is a physical contact. But the thing is, when we look at the way we will consider the collision phenomena, right, the actual physical contact is not a clear requirement. So means we will see that there will be some phenomena where there may not be an actual physical contact. Like, if you look at the collision between two billiard balls or collision between a ball and bat. Okay, all these are examples of what, even the other things that we discussed, right? All these are what examples of the collisions where we have physical contact. The bodies will really come into physical contact, right? So that is what is our general intuition whenever we say collision. But there are some phenomena which we will be considering as collisions, but there will not be a real physical contact. And one of the things, right, is what you might have already studied in your chemistry. In the alpha ray scattering experiment, right, Rutherford's experiment, what you see is that there will be the nucleus of heavy atoms like, gold foil. That is what he has considered, right? And the thin gold foil is bombarded with alpha particles. What are alpha particles? Helium 2 plus ions. Nucleus will be net positive charge, because it will be having just protons and neutrons, right? Protons are positive charge. That's why nucleus will be overall positive charge. Now, when the alpha particles are approaching the nucleus, right, both are positive, they will start repelling each other. So the alpha particle will get deviated even before it really goes and establishes the physical contact with the nucleus. There will be no real physical contact. Even before it gets the physical contact, it would get deviated, because the closer and closer it goes, right? Look at this. The interaction force, we also call it as what? Electrostatic force. What will be the electrostatic force magnitude? K Q1 Q2 by R square, because Q1 Q2 both are positive here. Okay, otherwise we would be actually putting a modulus symbol here, K into modulus of Q1 into modulus of Q2 by R square. Okay, so here both are positive, that's why we put it as what? K into Q1 Q2 by R square. As you see, as R is decreasing, right, means the charges are coming closer and closer. The F value will keep increasing. You can see as R is approaching 0, the force theoretically must be reaching very high values, right? As a result, the alpha particle would start getting deviated even before having a physical contact with the nucleus. So this interaction between the alpha particle and the nucleus, right, we also consider this as a collision. Okay, so while we talk about the normal collisions where we have a physical contact, we can also have collisions where there is no requirement for the physical contact. Okay, so this is something, maybe sometimes we can have some theoretical questions like this. Okay, so there may or may not be a real physical contact. So having the physical contact is not a clear requirement for the collision. Okay, now we said that the collision, we've been saying during the collision like that. So how do we see the actual collision process? So we'll see the collision process into 3 distinct and identifiable stages. So what is it? Let's say, for example, we'll talk about the collision between 2 balls, the one that we already seen in the visualization, right? Let's say we have one ball, another ball. Okay, so for the sake of simplicity, right, let us consider that this is at rest and this is the one that is actually moving. Okay, so what you see is that the time where they both are approaching means we talk about the relative approach. So as you can see here, let's number them 1 and 2. 1 is at rest, 2 will be approaching, right? So the time or the duration where the objects are relatively approaching to each other, that is what we call as the before the collision. And before the collision, there is no time limit. We can see from like 2 balls coming from very long distance, means you will see them coming, and then you will be able to observe it for that much amount of time. This has not got much significance in terms of the time. Okay, but before the collision means what? There will be a relative approach. What is going to be there? There will be a relative approach between these 2 objects. Now, once the first physical contact is established, because again we are looking at only the type of collision where we are talking about the physical contact getting established. Okay, so look at this. So there is a physical contact that is just established. From then onwards, what is actually going to happen, because every body, right, it will have some elastic behavior because of the molecular space, etc. Once they collide, what is going to happen is, if you try to zoom it and then look at it the micro level, right, the objects, they will start getting deformed because of the compression. So we'll see that what would happen is the objects, they both will start getting deformed because of the molecular level compression. And like the way a spring will expand back, right, they are getting compressed and then the spring expands. Similar in here, what is going to happen, the molecular compression, again they will try to come back to the original state. So this time duration, the molecular space is getting compressed and then coming back. This time duration, right, is what we will be calling as during the collision, and this is the one that is important. So this is the time, this time, right, this time delta t we are saying is a very small value. It will be in the range of a millisecond or a microsecond. Now once the molecular space have bounced back, right, we will see that the objects would now start relatively moving away. So we'll also say it as what, relative separation, means with respect to one, if you observe, right, relative velocity concept, if you bring, with respect to one, the other object will start appearing to recede or move away. Okay, so this is the final stage, which is what we call as the after the collision. Okay, this during the collision, right, since the duration is very small, this is a time duration, or this is the stage for which we will not be able to talk really much, because the duration itself is very small, right. We will not be able to talk very particular details about the during the collision time. So that is the reason why we will be trying to compare what is before the collision and what is after the collision. Okay, so we have three stages. One is the before collision, where we will see that there will be a relative approach between the particles. During collision, that deformation, and then the molecular spaces bouncing back. The deformation we are saying, right, in some cases what happens is the objects will be able to perfectly come back into the original shape, but in some cases they might not be able to. You will still see that there is some kind of an permanent deformation that will be left out. Okay, based on that we'll talk about it. Some energy will be lost, because when you create a permanent deformation, means what, there is energy that is lost in creating the deformation, right. So if it is able to come back to the original shape, means whatever the energy is spent in compressing the spring, if the spring is able to come back, means what, we are able to get all the energy, correct. So that is how we will be able to see what is going to happen to the energies of the particles. But this is about the three stages of the collision. One is before the collision, during the collision, and then after the collision. And when we talk about studying a collision, right, we will mostly focus on what, before and after. Why not during the collision? Because that is a very small time, right. We are saying the time is less than a millisecond, means we can't even really be able to study anything over there. Okay, now we have said that collision is an isolated event. So why are we calling the collision as an isolated event? Okay, so if we say isolated event, means there is no influence of any external forces, etc. Okay, that is what we call as an isolated event, right. And for an isolated event, remember in the Newton's second law, right, we talked about it. If you have one object or a group of objects, if the net external force is 0, means the total momentum will be what, conserved. So this is conservation of momentum. We have seen this comes from where? This comes from the Newton's second law, correct. Now let us see why for every collision the conservation of momentum, or the conservation of momentum principle, is going to be satisfied. If you look at during the collision, because that is what we have to focus now. Okay, so we have object 1, object 2. This is during the collision, means from the time they establish the first physical contact, they are going to undergo deformation and then come back. Now this delta t is a very small value, and we said as a result of the collision, the momentum of the particles will be changing. Let's say the change in momentum for the first particle is delta p1. If you divide this by the time of the collision, okay, then what is rate of change of momentum? The force acting on the particle 1. Similarly, if you look at the particle 2, it's got change in momentum, means divide that by the time taken, that will be what? That will be the force acting on particle 2. Now look at these values. Delta t is very small, means if we say delta t is in the range of microseconds, means 10 power minus 6 seconds. The change in momentum will be considerable, means it will be in the normal range. If you divide the change in momentum by 10 power minus 6, right, look at this, what will be the force, this force, right, which is the rate of change of momentum. We will also call it as what? The impulsive force. So look at these force values, they will be coming as abnormally high. I mean, we don't know what is the actual value of delta t. It's very difficult to find what is the actual delta t, but we know for sure that this will be in the range of microseconds, or that kind of a range, which means the impulsive forces that will be acting on the particles during the actual collision time, the impulsive force that will be acting on the particles, right, their values are going to be very high. The impulsive force values are going to be what? Very, very high. Now, other than this impulsive force, right, the objects may be having some external force influence, like maybe they will be experiencing gravitational force. There might be some external forces that will be already acting, but if you try to compare the magnitudes, right, with the impulsive force, it will be very much negligible. The impulsive force value will be what? Very, very high. So during the collision, the effect of these external forces, right, can be simply neglected. So on each and every, you take one object. On that object, let us say the impulsive force is in the range of 10 power 6 newtons. Just think about it. Impulsive force in the range of 10 power 6 newtons. What is the gravitational force? Maybe some, 500 newtons, 600 newtons. So the external forces acting on the objects, right, their influence during the collision time can be neglected. Why? Because in comparison to the impulsive forces, right, the value of this external force will be considerably less. That is why we can neglect the effect of the external forces during the collision time, and that is how we are going to consider the collision as an isolated event. Okay, so the reason why we consider this an isolated event is because the impulsive forces will be very high, because the actual time of collision is very less. That is the reason why if you divide the change in momentum by time taken for any of the particles, right, it will be coming abnormally high. Okay, and because the value is high in comparison to external forces, right, we can neglect the external forces. That is one. But we will have a doubt. There is impulsive force, right, which is very high. Then why are we saying the conservation of momentum principle? Why are we saying conservation of momentum principle? Because what are these impulsive forces? They are internal forces. What are the impulsive forces? They are internal forces, right? Look at it. When we say impulsive force is acting on object 2, that is because of what? Object 1 only, right? Impulsive force on object 1 means it is because of object 2. So the impulsive forces, they are what? They are action-reaction pair. They are basically what? The action-reaction pair, internal forces. So we are talking about the two objects together, means the impulsive forces is what we will be considering, and these are internal forces, these are not external forces, right? So as a result, what we will see, the net external force, since we are not considering the existence of any external forces because their magnitudes will be very small, right? We will see that the net external force we can equate it towards 0, and for the entire system we consider, means the conservation of momentum principle can be applied. Okay, so which means if you have say for example here the object m1 is having an initial velocity u1, m2 is having an initial velocity u2, and but here the u1 u2 are actually vectors, so we'll have to probably put a bar. And after the collision, let us say the velocities are v1 and v2, then what do you mean by the conservation of momentum principle? Initial momentum means what? m1 u1 plus m2 u2. Final momentum will be what? m1 v1 plus m2 v2. So this is what is the conservation of momentum principle that will be satisfied by all the collisions. Okay, so we are going to talk about the different type of collisions later, but for all the collisions, right, this conservation of momentum principle will be satisfied. Okay, so this is about the idea of conservation of momentum and why collisions will satisfy it. Okay, and also we have seen what is the reason why we call collision as an isolated event, because the external forces impact, right, will be negligible in comparison to the impulsive force acting on each and every body. Now we talked about what happens to the momentum of particles. Individual particles momentum might change, but as the system, whatever the total particles involved in the collision phenomena, right, the total momentum of particles before the collision will be equal to total momentum of the particles after the collision. Let us also talk about what happens to the energy of the particles in the collision. Now when we say energy, right, we are talking about the total energy. Okay, so this is something that some people will wonder as to why this is so, because the moment we say energy is also conserved, right, you might have seen in some textbooks or some places saying that some collisions energy will be conserved and some collisions energy will not be conserved. The point is, when we are looking at the energy here, we are talking about the total energy. So any collision process, right, if you look at the total energy of all the particles, total energy means what? We are including the mechanical energy, like the kinetic energy, potential energy, the internal energy of the molecules, excitation energy, radiation energy, the energy converted into the mass form, or vice versa. All these various forms of energy, if you include it, right, if you add up all the various forms of energies of the particles before the collision, we add up all the energies, that will be equal to what? The energies of all the particles after the collision. So we have to include all the types of energies. Okay, but the thing is, this is a very theoretical statement, because energy can neither be created nor be destroyed, right? Only it can be changed from one form to another form. Like say for example, when we see the collision of the two cars there, what actually happens? We'll see that a lot of sound comes. Okay, so maybe sometimes fire also will come. So the kinetic energy of the particles is converting into sound energy, or the light energy, etc. Like so the energy can be changing from one form to another form. But if you add up all the energies, right, the total energy of all the particles before will be equal to total energy of all the particles after. So here the thing that we need to look at is, even in +2, when we go to the modern physics chapter, right, in modern physics we'll talk about the collision between nuclei. If you look at the nuclear fission, what is nuclear fission? One large nucleus breaks down into smaller. We have nuclear fusion. Two small nuclei will be fusing into each other to produce a larger nucleus. So in these nuclear phenomena, right, some amount of mass will be converted to energy. Some amount of mass will be converted to what? Energy. Okay, so there we have to also take into account what is that energy converted into mass, or mass converted into energy. Okay, so those things we have to also consider. But the thing is, some of these energy terms, right, internal energy, excitation energy, radiation energy, each and every problem we will not be able to calculate all the things. That is why talking about the total energy, right, doesn't make much sense. It is true, we know that energy can neither be created nor be destroyed, but this will not be of use to us. What we will rather focus is on the kinetic energies of the particles. So instead of talking about the total energy, right, what we will be focusing on is kinetic energy of the particles. Okay, now we'll just look at one sample question. So this is the question based on the conservation of momentum, because whenever there is a collision, whether it is a collision between two particles, three particles, 4, 5, 10, whatever be the number of particles, right, the conservation of momentum principle will be always valid. So look at this, two particles 1 kg 2 kg undergo collision. Okay, 1 kg initial velocity. So look at this, we'll say m1 is 1 kg. What is the initial velocity for this? I plus 2j plus k. And final velocity, that is v1. What is the final velocity? 2i minus j minus k. What is the final velocity of the 2 kg particle if it has an initial velocity of I minus j? So let us call the 2 kg particle as m2. Okay, what is its initial velocity? I minus j. We have to find what is v2. I'll just wait for some time. So what is it? It is a collision that is happening, right? Initial momentum means what? Initial momentum of all the particles, m1 u1 plus m2 u2, that is equal to what? m1 v1 plus m2 v2. That's it. So we'll have to just take these values, substitute, and then find out the answer. Check it. What is m1? 1 kg, right? m1 is how much? 1 kg. So 1 into this u1, that will be as it is, I plus 2j plus k. m2 into u2, m2 is what? 2 kg into u2 means it will be multiplied by 2, plus 2i minus 2j will come. That is equal to m1 v1. m1 is 1, v1 is this, 2i minus j minus k plus m2 v2 means 2 into v2. So from here we have to just find out what is the v2 value. So look at this, there is a 2i on the left side, 2i on the right side, that will get cancelled. Okay, so now what else we have? There is a I on the left side, I. Then we have here 2j minus 2j, they will cancel. Right hand side we have a minus j. Bring it to the left, it will become what? Plus j. Then here we have a k, left hand side, right hand side minus k. Bring it to the left, it will become plus. So k plus k is what? 2k. That is equal to 2 times v2. Means what will be v2? Half of I plus j plus 2k. That is our v2. In fact, we can write it like what? Half I plus half j plus k. That is the final velocity of the 2 kg particle after the collision. Okay. Okay. So good, we'll move on to the next question. So this is another question. A man 60 kg jumps from a trolley of 20 kg standing on a smooth surface. Okay, so it's not jumps from, it's jumps onto. So there is a man. Okay, so he is having a mass of 60 kg. There is a trolley. Okay, so what is the mass of the trolley? It is a 20 kg. He is jumping on. Okay, so this trolley is standing. Okay, so this is at rest. He is jumping onto the trolley with the absolute velocity of 3 meter per second. Okay, so his velocity is what? 3 meter per second. He is jumping onto the trolley. Okay, so once he jumps means he will be coming and probably standing on the trolley, right? So once he is jumping means he will be coming and standing over here. Find the velocity of the trolley and the man together after the jump. Means what is it? It is like they both are moving together. After the jump, right, they both are moving together. So we need to find what is the velocity with which they both will be moving. Okay, so what is it? If you look at the initial case, right, initially what is the momentum? There is only going to be momentum for the man, right, because the trolley is at rest. So he is jumping with absolute velocity of what? 3 meter per second. So momentum will be what? 60 into 3. Everything is in the SI system. Okay, so that will be what? 180 kg meter per second. Now after he jumps onto the trolley, they both are moving together. It's like what? The man is 60 and the trolley is 20. Totally that is moving with the velocity v. Let us say v is what we need to find. So what is the final momentum in this case? Total mass is what? 80 into v. That's it. Because conservation of momentum has to be satisfied, right? So what is it that we have? 180 kg meter per second is equal to 80 kg into v. The kg will get cancelled. 10 18s are 10 8s. So 18 by 8, which is what? 9 by 4 meter per second. That is our v value. It's a straightforward question. So there is a man who is jumping onto the trolley. So initially the trolley is at rest. After he jumps onto the trolley, they both are moving together. So we need to find what is the velocity of the trolley and the man together after the jump. Okay. So look at the next one. A moving body of mass m and velocity 3 km per hour collides with another body which is at rest, having a mass 2m and sticks to it. Means what? M 2m. This is moving with how much speed? 3 km per hour. This is at rest. After collision, what is happening? They are sticking and moving together. It's like what? Totally m and 2m, totally it will be what? 3m. They are moving together. Okay. What will be the velocity of the combined mass? They are sticking and then moving together, right? After some time, we will see that this will be a particular scenario in the collision. So we'll see, under what conditions after a collision the objects will stick and move together. Means they will be moving with a common velocity. That is it. Okay. So here we need to find what is that common velocity v. Again same thing. Look at the initial momentum. What is the initial momentum? This is moving, but 2m is at rest. Means m into 3. That is the initial momentum. Okay. So here velocity value, right, is going to come in terms of kilometer per hour. Okay. Final, what is the momentum? Both m and 2m are moving together with the common velocity v, right? Means it will be what? 3m into v, because the total mass is now 3m, right? M plus 2m is what? 3m. That is moving with the common velocity v. Okay, that is the final momentum. Conservation of momentum principle means what? M into 3 is equal to 3m into v. 3 gets cancelled, mm is cancelled. So what is the v value? Numerically 1, but what will be the unit? Kilometer per hour, right? So what is the answer for this? Option C. Check it, guys. So all these questions, right, we are using the basic principle, which is the conservation of momentum. So whenever we say collision, right, any type of collision, it is going to satisfy this conservation of momentum principle, because the collision as such we identify it as what, an isolated event. Okay, now we will talk about the classification of collisions. So the collisions, right, we'll try to classify based on two parameters. One is the based on the direction of motion of particles, and the other type is based on what will happen to the kinetic energy of the particles. So what are the two bases on which we will classify the collisions? One is the first basis is what, based on the direction of motion of particles, we will classify the collisions into different types. And second basis is what, based on what is happening to the kinetic energies of the particles. So when we say what is happening to the kinetic energy of the particles, means we are going to compare before the collision what is it, after the collision what is it. Okay, so this is what we will be trying to compare. Now the first basis, what is the first basis? Based on the direction of motion of particles, right? Look at this, the example that we see here, right? So the m1 is moving with a velocity u1, m2 is moving in the same direction with a velocity u2. The directions of the particles are in the same line. Okay, now obviously if u1 is more than u2, right, means it's like m2 is going towards the right, m1 is also going towards the right, but m1 is coming faster. Eventually they will collide, and what you will see after the collision is the m2 will start going with a higher speed in comparison to m1. Okay, so here what do you observe? All the velocities, right, u1, u2, v1, v2, they are all present along the same line. Now even the second scenario, you see what is here, m1 and m2, they are like approaching each other. So the initial velocity directions are what, opposite. In the case A, what do you see? Initial velocities are in the same direction. Case B, what are we observing? The initial velocities are in exactly opposite direction. Okay, now here also they will collide, and after collision, depending upon the velocity values, either they may move in the same direction or they may move in different directions. We'll see multiple scenarios can happen. Okay, but here also what we generally observe is that the objects after the collision, right, they will be still keep moving in the same line. Now when we say same line, right, a line can have two possible directions. Line means what? There can be two possible directions. When this situation comes is, if you look at these objects colliding, right, if you look at the objects colliding, the velocities of these objects are along the center line. The velocities of the objects are in the center line, means this is the center of particle 1 or object 1, this center of object 2. Whatever the center line we see, right, the velocities will be along the same center line. If that is the case, then such a collision, right, before the collision as well as after the collision, we will see that the velocity of the particles will be all confined to one line. Okay, and that is going to be what, the center line of the particles. Such a collision is what we will be calling as either a one-dimensional collision or a head-on collision. So what is the main requirement for the 1D collision or head-on collision? The velocities of the particles, right, before the collision, if you look at it, they should be along that center to center line. If they are along the center to center line, means what is going to happen after the collision also, right, because the impact of collision will be along this center line. The impact of collision, right, will be along the center line. After collision also, we will see that the velocities will be confined to same line, because the line means we can have two possible directions. Okay, but the velocities will be confined to that same line. Such a collisions, what do we call them as? We will call them as head-on collisions or one-dimensional collisions. Why are we using the word one-dimensional? Because all the velocities will be in the same straight line, right? That is why we call it as what? One-dimensional collisions. Okay, there is one more thing that we need to look at, particularly for the head-on collisions, right? If you look at the actual collision, when it is about to collide, the two surfaces the surface of object 1, surface of object 2, you'll see that they'll be having a contact. They'll be having a contact. Okay. Now the normal to the contact surface, right? Normal to the contact surface will be the line of velocities. So whenever we talk about the head-on collision or 1D collision, the center to center line will also be what? It will also be the line which will be the common normal between the contact surface. So when the collision is happening, there will be that common normal, right? So common normal also will be what? The center to center line. So this is what is the head-on collision or the one-dimensional collision. Okay, and now we'll try to study mostly about this head-on collision. Okay, the other type of collision is when we have say for example, look at this. So the object is coming along this line, it is colliding with the, let's say we number them 1 and 2. After collision, what is happening? 2 is going like this and 1 is coming in a different direction. So here the velocities of the particles, right, they are not confined to a single line. The velocity of the particles, they are not confined to a single line. They may be in a plane or they may be even in a 3-dimensional space. Such collisions, we call them as oblique collision. Means, the velocities will be making an angle with respect to each other. Okay, so such collisions are called as what? The oblique collision. So we'll see that there is also a reason why we will call it as oblique collision, like we said, right? So we have two objects colliding. Now the normal line for the contact surface, we will draw the normal line, the common normal, right? The velocities of the particles before the collision, the velocity of the particles, right, will be making some angles with the common normal. So in case of head-on, what happens? The velocities will be along the common normal line. In case of oblique, the velocities will be making some angle with the common normal. That is how the word oblique also is used. Okay, and we will see that here the motion will not be confined to a straight line. It may be in a plane or it may be even in a 3D space. So this is how we will classify the collisions based on the direction of motion of the particles. Okay, so one is the head-on, that is also called as the one dimension. Other one is the oblique. Okay, now we can see how this oblique can be represented, right? So we'll see the representation of the oblique here, oblique type of collision. So the velocity is, right, so here the center, the velocity u1 and velocity u2, they are along different lines. You can see the velocity u1 and u2 will be along different lines. So when the m1 is actually coming and colliding, this is the normal line, this is the normal line, right? So you will see that the velocities are actually making some angle with the normal. So you will not have the velocities along that common normal line. That is the reason why after collision, what is your observation? They will be moving in different directions. Okay, so we'll look at some examples of the oblique collision, and generally sometimes in JEE Advanced, right, they will give us some particular scenario, maybe typically these paragraph questions like that. We'll have these oblique collision problems that can be given. Okay, so this is about the oblique collision. Now the collisions can be also classified on the second basis. What is second basis? Based on the kinetic energy of the particles. Okay, so instead of saying based on kinetic energy of particles, we can say based on what happens to the kinetic energy of particles. Because if you look at the collision, right, we said we'll focus on before the collision and after the collision. So if you have the total kinetic energy of all the particles before the collision equal to the total kinetic energy of all the particles after the collision, such a collision is what we will be calling as a perfectly elastic collision. Like we talked about the collision of a gas particle with the walls of the container or with the other gas particles, right? All these are what? Perfectly elastic collisions. If there is a difference. The initial kinetic energy is not equal to final kinetic energy. Generally what happens is the final kinetic energy will be less than the initial, means there will be a loss. Generally what happens, there will be a loss in kinetic energy. The amount of energy that is lost will be converting into either in the form of sound or heat or light, all the things that we talked about. Okay, so such a collision is what we will be calling as inelastic collision. So what is it going to be called as? Inelastic collision. Okay, now the scenario where we'll have the kinetic energy loss maximum, because we said generally in inelastic collision there will be a loss of kinetic energy. Loss of kinetic energy, why? Because final kinetic energy will be less than the initial value. But in a particular scenario, the loss of kinetic energy is going to be maximum. That scenario is what we will be calling as a perfectly inelastic collision. So whatever the scenario where we will be having the kinetic energy loss maximum, right, that will be called as what? Perfectly inelastic collision. Okay, so inelastic collision, what we said, generally the final kinetic energy will be less than the initial, but we can also have some special cases where Ke final may be more than Ke initial. For this what should happen? The object during the collision, right, some of its internal energy, maybe in the form of chemical energy or something, some of the internal energy should come out in the form of kinetic energy. Some of the internal energy of the particles, right, should be coming out as the kinetic energy of the particles. Then only the final kinetic energy will be more than the initial. But otherwise, generally when we talk about inelastic, means what? The final kinetic energy will be less than the initial kinetic energy. Okay, so this is how we can classify the collisions based on what happens to the kinetic energy of the particles. Okay, now when we look at this, right, it is like forming a matrix, isn't it? So we have based on the direction of motion of particles, we have head-on or 1D and oblique. Based on what happens to the kinetic energy of particles, we have these three categories: perfectly elastic, inelastic, and perfectly inelastic. Perfectly inelastic collision, right, can be also called as a plastic collision. Perfectly inelastic can be also called as what? Plastic collision. Okay, so we'll see that there will be totally how many? 6 categories. We can have head-on, perfectly elastic; head-on, perfectly inelastic; head-on, inelastic collision; or we can have oblique, perfectly elastic; oblique, inelastic; oblique, perfectly inelastic. Like this we can have totally how many scenarios? We can have 6 cases that we will discuss. But mostly, right, we will try to focus on the head-on and oblique, perfectly elastic. Okay, so these two are the things that we will be focusing. I mean, we will cover the others also, but this is where we will be trying to give more focus. Okay, now before we go and discuss the types of collisions one by one, so now what we'll do is we'll go to each and every type of collision. We'll see how the conservation of momentum principle can be applied and how we will be able to understand the change in kinetic energy of the particles, if there is any. Okay, so otherwise if it is a perfectly elastic, means we'll have one more condition: kinetic energy initial is equal to kinetic energy final. So we'll see how these things will be applied in each and every type of collision. But before we go there, we will discuss about one important quantity, which is called as coefficient of restitution. Coefficient of restitution, right, it is a parameter that tells us what is the impact of collision on velocities of particles. So we'll say it tells us what is the impact of collision, or what is the impact of the impulsive forces on the velocities of the particles. Okay, now the coefficient of restitution, right, can be defined for both the head-on type of collision as well as the oblique type of collision. But we will see that the use, or rather importance of this, right, will be more in the case of the head-on type of collision. But the coefficient of restitution can be defined for both head-on type of collision as well as the oblique type of collisions. But we will see that the analysis using the coefficient of restitution, right, will be more meaningful when we talk about the head-on collision. Okay, so let us see what is this coefficient of restitution. Here we will try to define it for the head-on type of category. So look at this, the example for the head-on, right? Let us take this M1, M2. Okay, so M1 is moving with the velocity U1, M2 is moving with the velocity U2. Now when they both will collide, when U1 is more than U2, right? In the way we are represented, when U1 is more than U2, the M1 will come and hit it. So here the relative velocity of approach. What do you mean by that? Look at it now. So we'll just start with some simple numbers. Let us say this is 2 meters per second. This is some 6 meters per second. If I ask you what is the relative velocity of approach, means what is it? It will be U1 minus U2, 6 minus 2. Correct. Now after the collision, what is going to happen? Look at it. This M2, it will start moving faster. If M1 is also moving in the same direction, it will slow down. So let's say for example V2 is now 7 meters per second. These are just sample numbers, okay, and V1 is some 5 meters per second. Now if we ask what is the relative velocity of separation after the collision, because before the collision what is going to be there? Relative velocity of approach. Here what will be there? You see, what is the relative velocity of separation? Means 7 minus 5, right? That is what? That is V2 minus V1. The coefficient of restitution, right, in case of the head-on type of collision. So why we are emphasizing on the head-on is because in head-on, right, the center to center line or that normal line will be the line along which the velocities are also present. So the impact of that impulsive force, right, will be directly along the line of these velocities. So here we will be able to see clearly what will be the impact of these collision forces on the velocities of the particles. That is the reason why we said the analysis using the coefficient of restitution, it will be more meaningful in case of the head-on collision. Now the coefficient of restitution is defined as the relative velocity of separation after the collision. So how it is defined? As the relative velocity of separation after collision divided by the relative velocity of approach before the collision. So which is what? Relative velocity of separation after the collision means that is V2 minus V1 divided by relative velocity of approach before the collision means what? U1 minus U2. Now while we have taken an example to discuss it, right, here in 1D collision, like the way we do in kinematics, right, if the velocities in one direction are taken as positive, because here we'll have only velocities in one line, means either they will be like towards the right or towards the left. If you take one direction to be positive, right, other direction we have to take it as what? Negative. That's the sign convention we follow in kinematics also, right? If you take, so here these equations, right, we'll have to use the equations by following the sign convention. Means what? One direction you take positive means other direction values you have to take it as what? Negative. Now we'll see that when we are going to discuss about the head-on type of collisions, because in head-on we'll have three, right? Head-on perfectly elastic, head-on inelastic, then we have head-on perfectly inelastic, correct? So when we go and discuss about these three types of collision in head-on, we will see that the coefficient of restitution value, right, will be changing. How it changes we will be able to understand. Okay, so this is about the coefficient of restitution and why its significance is more when we talk about the head-on, because the line of velocities is same as the line of the impulsive forces. So the impulsive force will be acting along that common normal line, that is same as the line in which the velocities of the particles are present. Okay, so this is about the coefficient of restitution for the head-on type of collision. So when we go to oblique, right, there we will see what will be the way in which we will define the coefficient of restitution. Okay, so we'll just wind up the session with this particular problem. A moving block having mass m collides with another stationary block having mass 4m. So look at this, mass m It is colliding with 4m. This is at rest. Stationary means what? This is at rest. Okay. The lighter block comes to rest after the collision when the initial velocity of the lighter block is v. Then the value of coefficient of restitution is how much? See what is happening after the collision, right? The lighter one is coming to rest and the heavier one is moving. 4m will start moving. Initial velocity of the lighter block is what? V. So we need to find the coefficient of restitution. So what we'll do is we can just call it as, this is 1, this is 2. Correct. So what is the E formula? V2 minus V1 by U1 minus U2. So here look at it. No, what is the U1 value? The m is coming with the velocity v initially, that is v. Okay. U2 is what? Initially the 4m is at rest, so U2 is 0. Then V1, what is V1? They are saying that the lighter block is coming to rest after the collision, means V1 will be what? 0. We have to find what is V2, because V2 is what? Unknown. Correct. So the V2 is what we need to find. So how do you find V2? We have only one relation. What is it? Conservation of momentum. Apply it. M into V plus 4m into 0 is equal to m into 0 plus 4m into V2. Okay, so the zeros will just cancel off. So m will be cancelled. V by 4 is equal to V2. What is V2 value? V by 4. Okay, that's it. We'll just have to substitute. V2 is what? V by 4 minus V1 is what? 0. Divide by U1 is what? V minus U2 is 0. So V by 4 divided by V, that is what? 1 by 4, which is 0.25. So what is the answer for this? 0.25. Okay, so what we are doing here, just using the conservation of momentum, we are able to get what is the V2 value, the velocity of the 4m, because m is anyway coming to rest after the collision. Only 4m is having velocity. We are able to find what is the velocity of the 4m using the conservation of momentum. Once we get it, means straight away go and substitute in the coefficient of restitution formula. That's it. Okay, so with this we'll hold it here, and in the next class, right, we'll specifically go into each and every type of collision. Like we'll start with head on. In that we'll have 3 cases. Then oblique, we'll have 3 cases. We'll start discussing about them in the next class. Okay, we'll see in the next class.